So first of all, what are microservices? This chapter is an introduction into the microservices architectural style and the impact on how you may be used to designing your applications at present. First, I'm going to go into what microservices are, providing you with a definition, and then a more in-depth explanation, mainly by using a monolithic application as a way to compare and contrast the microservices approach. And then we'll look at practical applications of the pros and cons of using a microservices architecture and what kind of things that you need to think of above what you are currently considering with a monolithic application. So what are microservices anyway? Well, at present, there is certainly a lot of industry hype around this topic. And to me, it seems like our industry goes through this every few years. A new technology comes out, and it takes several years to sort it out and learn what it really is all about. Microservices are best described as an architectural style for building applications. The best way to understand this style is to contrast it with something most developers are familiar with, the so-called monolithic applications. In fact, I'm going to walk you through a compare-contrast exercise in just a bit. So microservices are an architectural style where a single application is built not as a single application, but as a suite of small services, each of which is running as an independent process, and each of which communicate with the others through some type of open or at least well-known protocols, with all of the benefits and risks that this approach applies. The industry experts have provided their definitions for this new term. The first quote is from Martin Fowler, and you can see that this is basically the same as what I've just described. Single application, built from independently running services, communicating using open, lightweight techniques. Another great simple description, almost a soundbite, comes from Adrian Cockcroft at Netflix, fine-grained SOA. Service-oriented architecture has been with us for quite a while now. This is taking it down to the application level. However, there are some very important differences which I will point out later. For our course here, this is the definition we will use. Microservices are about building individual applications as a suite of smaller services. This is in contrast to having a single monolithic application or executable. Each of these services runs as an independent process. So services are not merely modules or components of code within a single executable. They actually execute on their own. Microservices intercommunicate with each other via open or at least widely understood protocols. Things like HTTP and REST, or AMQP messaging, or TCP, or even FTP. Microservices are separately written, separately deployed, separately scaled, and separately maintained. In fact, they may be written in different languages. The services are used to encapsulate business functionality, not really technical functionality. They represent a different way to encapsulate functionality as opposed to whatever language constructs that we're used to, such as packages or classes or jars or whatnot. The services themselves are independently replaceable and upgradable, which stands to reason since they are separately maintained applications. Probably it's best for us to go on record to describe what microservices are not. Microservices are not the same as service-oriented architecture, though it certainly may seem so at first glance. SOA, or service-oriented architecture, is about integrating various enterprise applications. Microservices are about the design of single applications. Microservices are certainly not going to be the solution to all of the problems that you're facing right now. The truth is there are situations where the microservices approach would introduce serious drawbacks and risks, and you should know about these. And finally, though it is a new buzzword in the industry, microservices are not necessarily new. It is possible to find many cases of existing applications composed of separate, independent, intercommunicating processes, and it is possible that you yourself may be working or have worked in the past on applications that have embraced the essence of what microservices are all about. Microservices are certainly a big trend now. And one of the reasons we are hearing so much about them is because big, visible industry players have been deploying them with great effect. Twitter has described their recent activities as adopting a microservices architecture. They were utilizing a Ruby on Rails monolith, and they have chosen to decompose it into microservices, usually still written in Ruby on Rails. Facebook has described their movement away from a simplistic PHP monolith to microservices. And probably most visibly, Netflix has done a great deal of work to eliminate their monolithic Java applications in favor of smaller, independent microservices. So that is our working definition of microservices, but it might not do much for helping you understand exactly what they are. So let me now take you through a more practical explanation by exploring a traditional monolithic application, and then we can see how microservices are different by comparing and contrasting. So let's start by thinking about a traditional shopping cart application, something with a web interface. If you stop to think about the functional areas of an application, you can probably think of several predictable items. We need a way to search for products. We need a way to store all of our products in some kind of catalog, probably in concert with some type of inventory management. We have to let customers put items into shopping carts and go through a checkout process. And we have to think about order fulfillment and a number of other items that we don't have listed here. So before I show you how this would look in a microservices architectural style, let's take a look at how a traditional monolithic application would look. For a monolithic style shopping cart application, we would probably take the familiar layer cake approach backed by a traditional relational database. We would have data access objects talk to our database to handle persistence. We would have our use cases implemented by our service layer to the extent that we can, and we would have a controller layer serving up traditional web pages to traditional web browsers. We might even have some dynamic JavaScript code on our pages talking to the controllers too, but everything is basically represented by this layered architecture. Now, if you take a closer look at those layers, you can see a lot more detail. There are many different kinds of controllers for the different pages in the application, like the search page and the product review page and the cart display page, the entire checkout process, and the contact us area of the site. The service layer attempts to model our use cases, and we probably have separate services to control search functions and catalog management functions and review functions and cart functions and so on. At the DAO layer, or repository layer, depending on what you want to call it, things resemble the data model as it's expressed in the database. And there are typically DAO objects representing each table, or perhaps a small group of interrelated tables. So we have DAOs for products and inventory and cart and customers and so on. And you can expect that within the database we have various tables set up to support the storage needs for the various parts of the application. You could probably extrapolate accurately what the data model looks like without even having seen it based on this diagram here. Now this application structure here is well organized and it's well understood. So why is there a move or interest in moving to something different? Well, let's start to think about some of the challenges that we are facing at present in the industry. 10 years ago, and this is recorded in 2015, so think back to 2005. 10 years ago, we only had to think about web interfaces, but now we have a proliferation of client technologies. We have smartphones, which are widespread. We have tablets. We have game consoles and TVs, and now we even have watches and wearables. And who knows where we're going next? The controllers that were designed for our web interfaces were not designed for these other channels. Plus, we have to think about the different kinds of networks, like mobile networks, that might be more sensitive to chatty interfaces. We also have to think about different types of persistence and back-end technologies. 10 years ago, mostly everything that we stored in a relational database. And these databases have been fantastic one-size-fits-all solutions for us for many years, throughout my career, I would say. But now we have access to a lot of specialized technologies that offer really superior performance for specific use cases. For example, think about our product search. Our product search is going to be much faster and much more robust if we can get it out of a relational database and use something like Elasticsearch. Things like the product reviews are stored more flexibly in a document store like Mongo. And plus, with something like Mongo, we don't have to worry about things like schema changes. The shopping cart, it's a lot faster and simpler if we use a simple key value store like Redis. Plus, we still have needs to access legacy back-end technologies like, let's say, SAP for our orders and shipping. And we might decide it's much easier to let PayPal handle all the payments for us. Now, please don't think from this diagram here that relational databases are going away. They are still the Swiss Army knife of storage technology. The point here is that we are more likely to embrace a plethora of back-end technologies, and our single application written in a single language will have to stretch a bit to accommodate all the various needs. For one thing, I'll have to have all of the jars and supporting libraries for all of these technologies in a single executable. Here's another thing to think about. Our monolithic code base is a single application. It's a single code base. Now, if it's small enough, it's pretty easy for a single team to implement features, say from a list of features here, a backlog, and it's relatively easy to manage source using source code management, and it's fairly easy to test and deploy, hopefully using some type of newer technique like a continuous delivery pipeline. But here's the problem. What if the system is large and complex? And what if there are a large number of features that need to be implemented reasonably quickly? Well, we're going to need a larger team. And inevitably, we'll have a large code base. And large teams are hard to manage, and so are large code bases. So the predictable response here, from a management perspective, is perhaps what we'll do is we'll break up our big team down into little teams, each one working on a subset of features, and each one dedicated to maintaining their separate code base for a single module of a large application, something like a jar. Well, this approach might mean that we need to have a separate team in charge of assembling our separate modules into the completed application, and then subjecting the entire thing to our continuous delivery pipeline. Here's the problem. There's actually several problems here. A big problem for all of this is what happens when a flaw is discovered late in the pipeline, such as user acceptance testing. Now we can't deploy the application until we fix that problem, or at least back it out. Then the problem is that the assembly team is continually working out to try to find out the best version of each team's components to deploy to get the optimal delivery of features versus the quality that we need. And then they will be putting pressure on the original teams to fix specific issues in specific versions of specific modules. So this can quickly become a big mess. And most of this has nothing to do with coding, but assembling and deploying a large application. So the monolith is a single application executable. And there are advantages and disadvantages to this. One advantage is it's actually quite easy to comprehend a single executable, even a large one. After all, that layer cake diagram I showed a few moments back was it's pretty easy to determine which piece lived where. But it is not easy for an individual developer to digest the entire thing. There will be code specific to different devices and different storage technologies and so on. Plus, there's going to be millions of lines of code. Also, we're pretty much committed to working in a single language. If we started this in PHP, we're going to need to do everything in PHP. If we did it in Java, it's Java from now on. There could be other languages, frameworks, and technologies for any individual piece that might work quite a bit better than what we are currently working on now and committed to. But we can't try it out because we're committed. Next, the ability for us to modularize our application is really subject to the capabilities of the language or the framework that we've chosen. If it's Java, then we use packages and classes and jars and wars. If another technology comes out that suits our needs better, well, we're just stuck. We also have to make our language and framework of choice work with whatever storage and service technology we are working with. Fortunately, in Java, we usually have a reasonable alternative for almost everything that's out there. Almost everybody provides a Java interface for what they're doing. But imagine if we had to do some part of our system's work in something like SharePoint, Microsoft SharePoint. Well, if so, .NET is clearly going to be the language of choice for that part of the system. But with a monolithic application, I'm stuck with whatever we're using for the entire application. So the advantages of monoliths is that they are easy to comprehend, though not really digest. They are also reasonably easy to test as a single unit, at least until they surpass a certain threshold. They are also pretty easy to deploy as a single unit. I can deploy version 1.5 of my app as a single WAR file, and everything is included in that one WAR file. They are easy to manage, at least until they get to a certain point, and changes are easy to manage too, actual change control. Again, at least until a certain point. Once we get to a certain point, change control begins to be a little bit of a headache. Scaling is also straightforward. As long as you abide by some basic principles, you can put most web apps behind a load balancer and scale it as needed. Managing complexity is left to the constructs of the language we are using, and we usually have good languages and frameworks for handling this. But here are some drawbacks. Number one is the language and framework lock. Our app is committed to a single technology stack forever. If there are portions that could benefit from another technology, we are basically trapped, and we are facing a rewrite situation. We also don't have the freedom to experiment with different technologies. We have to make wholesale adoption. Next is digestion. A single developer cannot digest a large code base. It just can't happen. There are too many things to know. There's too many secrets to discover. Because of this, a single team cannot manage a single large code base. And a large team has its own challenges, as any project manager can tell you. In fact, Amazon has a term for this. They have something called the two-pizza rule, which basically says that if you can't take your team and feed them at lunch with 2 pizzas, then it's just too big. Deployment as a single unit is great for testing and versioning and manageability, but we become unable to independently deploy a small change to a single component. And as a result, all of the changes get held up until basically, think of a bus schedule. You're basically waiting until the next bus comes by. And this affects our ability to rapidly deliver value, the way the agilists and the continuous delivery people are talking about.